Greetings to everyone. Myself, Dr. M. Harivanan, working as an associate professor in the Department of Civil Engineering in Mari Lakshman Reddy Institute of Technology and Management. It is an autonomous institution which is located at Dundikal, Hyderabad. I am handling the subject of surveying and geomatics to the second year civil engineering students. So today we are going to start our third unit, that is theodolite surveying. Okay, we are having the syllabus like this, that is types of theodolites, fundamental lines, temporary adjustments, measurement of horizontal angle by repetition method and reiteration method, then measurement of vertical angle, trigonometrical leveling when base is accessible and inaccessible. Along with that, another topic, that is traversing, methods of traversing, traverse computations and adjustments, then omitted measurements. This is the syllabus we are having under the third unit. So first we should discuss about theodolite surveying. So we have been measuring horizontal angles by using a compass with respect to a meridian. Okay, so in some cases if we need the vertical angle, or else if it is magnetic field area, okay, now the compass won't give the exact reading. Okay, now it won't give accurate reading. That time we should go with, or that time we are in the situation to get the accurate result. Okay, now so during that time we can go with the theodolite. Okay, now so theodolite is an instrument to get the both horizontal angle as well as vertical angle, and also it won't the affect by the magnetic field, and also we can, with the help of measurements, we can get the distance also by doing indirect calculations. Okay, so when the objects are at the considerable distance and are situated at a considerable elevation or depression, then it becomes necessary to measure horizontal and vertical angles more precisely. So these measurements are taken by the instrument known as theodolite. Okay, so wherever we can't use compass, okay, now for measuring the horizontal or vertical angle, and in order to measure the distance, okay, now that time we have to use the theodolite as an instrument which we can get the horizontal angle, vertical angle, as well as the distance between the points with the help of some indirect method of calculations. Okay, next, what is theodolite surveying? The system of surveying in which the angles and the distance are measured with the help of an instrument called theodolite is known as theodolite surveying. Okay, next, classification of theodolites. So based on two categories the theodolites are classified. The first one is based on horizontal axis, so that on the horizontal axis we are having some base so that we can rotate it easily. Okay, so that is called transit theodolite and non-transit theodolite based on the rotation. If with respect to horizontal plane the theodolite is to be rotated, then it is called transit theodolite. If not rotated, then it is called non-transit theodolite. Then next, based on angle. Okay, so we are having some angles to measure the uh, angular measurements. Okay, now so that the first one is Vernier theodolite, second one is micrometer theodolite, then third one is electron digital theodolite. So first category based on horizontal axis. So transit theodolite. A theodolite is called a transit theodolite when its telescope can be transmitted or transited. Okay, now that is, it can be revolved through a complete revolution about its horizontal axis in the vertical plane. Okay, so in the figure, this is our telescope. Okay, now, so this setup we can rotate in the direction both clockwise and as well as anti-clockwise. Okay, now, so if I'm going to revolve entirely, okay, and the telescope, okay, now whatever it is with respect to the axis, okay, now we can rotate or we can transit along the horizontal with respect to horizontal axis. Okay, now then it is called transit Totolite, either upward or downward. Okay, now, so this is called transit Totolite. Next, non-transit Theodolite. The telescope cannot be rotated. Like our dumpy level, the telescope should be kept in a single place. Okay, now it won't move anywhere, or we cannot rotate anywhere. Okay, now, so that type of theodolites are called as non-transit theodolite. Next, based on angle. Okay, here for getting the angular measurements, okay, now the reading of the graduated circle is in verniers. Okay, now vernier scale, then that kind of theodolites are called vernier theodolite. Okay, here in the figure we are having the vertical circle here. Okay, similarly we are having the horizontal circle here. Okay, now this position, so in these positions we are having some angular values. Okay, now in horizontal plates it is 0 to 360 degree, but in the vertical vernier scale it is 0 to 180 degree. Okay, now, so this is called vernier scale. Okay, now, so we are going to read these values directly with the help of eye. Okay, now, then micrometer theodolite. If a micrometer is provided to read the graduated circle, okay, now then that kind of theodolites are called as micrometer theodolite. Then third one, electronic digital theodolite. Okay, now, so instead of reading ourselves, okay, now reading by ourselves, the reading has been displayed directly in the form of digital. Okay, now that kind of theodolites are called as electronic digital theodolites. Okay, now, for example, our total station is the advancement in the electronic digital theodolite. Okay, so in general, we are going to use transit vernier theodolite. Okay, all over the world for doing the works. Okay, so some of the uses of theodolites are listed here. So measuring horizontal as well as vertical angle has to be done with the help of theodolite. Second one is locating points on a line. For example, uh, here the station points A and B are there. Okay, if like a ranging process. Okay, now if I want to place an intermediate points, okay, now if I'm going to do the ranging process, that will may get some error by fixing the intermediate points. But if I'm going to place a theodolite here and I'm going to arrest my horizontal movement, okay, now automatically I can get, okay, now, so this is my station point A I can consider. So if I'm going to fix the instrument somewhere here, okay, now somewhere at center, so that I can view both the points B as well as A. Okay, now, so that by doing the transit, okay, now by rotating the telescope towards A and towards B, okay, now, so that I can make the intermediate points very easily. Okay, now, so that is our second point. Then third point, prolonging the survey lines. So if I want to extend this line, okay, now beyond the B or beyond the A, I can extend it easily with the help of transit theodolites. Okay, now, so that is one advantage. Then third one, finding difference of level. So obviously with the help of theodolites we can find the difference of elevation between the points. Like a dumpy level we can use theodolite also. Okay, then setting out of grades. Okay, then ranging the curve. So when we making the curve profile, okay, no, in the road alignment, road or railway or canal alignment, whatever it is, okay, no, we can make the alignment that is smooth curve, okay, with the help of theodolite easily. Okay, then last one is tachyometric survey. So whenever we can't access the position of a point, okay, now, so that time I'm in the situation to get the distance between the two station points, okay, now, so with the help of elevation, that is leveling staff reading, and corresponding to their angle, I can get the distance between the two stations points, that is called tachyometric survey. So these are all the things I can do with the help of theodolite, and this is the uses of our theodolite instrument. Next, sectional view of a theodolite. Okay, now, so here it is the sectional view of the theodolite. So first one is vertical axis, which is nothing but if I'm going to rotate my telescope, and it should be at 0 degree, okay, now, and then at the time whatever the axis passed to the ground, that is called my vertical axis. Second one is object. So here there are two attachments in the telescope. One is object piece, another one is eyepiece, okay, now, so with the help of object piece, we can view, okay, now, with the help of, sorry, we can, whatever the element we are going to focus through the telescope, that is called the object piece. Whatever the element we are going to see through the telescope, that is called the eyepiece, okay, now. Then third one is telescope. So this is the component of consisting of both the object piece and eyepiece is called a telescope. Okay, now, uh, then next one is altitude bubble. The altitude bubble is to be fixed on the vertical circle, near the vertical circle. Okay, so here it is the vertical circle. Okay, now nearby that we have the altitude bubble. So if whatever the reading we are going to do with vertical axis, or if we are going to measure the vertical angle, okay, now that time we have to do the temporary adjustments with respect to this altitude bubble. Okay, then next one is vertical clamping screw. So for if I'm going to tightening the vertical clamping screw, automatically the telescope won't move from its origin position. Okay, so likewise, so for this purpose we are going to use vertical clamping screw. Then Trunnion axis, the axis which passes through the telescope and to its vertical axis is called a Trunnion axis. Okay, next vertical circle. So it consisting of 0 to 180-degree angle, so that we can use it to measure the vertical angle with the help of Vernier scale. So for that we are using vertical circle. Next eyepiece, plate level. So here one level, one bubble tube is there. Okay, that is called plate bubble or plate level. So whenever I am going to deal with or I am going to measure horizontal angle, okay, no, that time I have to level this bubble, okay, now, or this bubble tube. Okay, next upper plate. As like our dumpy level, the upper plate and lower plate arrangement we are having here. Okay, now, so upper plate consisting of vernier A and vernier B. Okay, and the lower plate we are having, the next one is inner spindle and outer spindle. This one is tri batch. This is the setup we are going to connect the instrument with the upper plate. Okay, then leveling screw. This tri batch setup having the leveling screw in it. Okay, now, so by adjusting the leveling screws, there are three leveling screws are available. Okay, now, so by adjusting this leveling screws, we can make the bubble tube as well as the altitude bubble, okay, now, into its center position. Okay, next trivet. Okay, then tripod head, then tripod leg. So over the tripod leg we have to place our instrument. Okay, so without tripod, we can't do the measurements with the help of theodolite. Next, details of upper and lower plates. So in upper plate we are having vernier A and vernier B. So always the main scale reading. Here we are having 0 to 1 360-degree angle. Okay now. Here the least count is 20 minutes. Sorry, the least count is 20 seconds. Okay. So vernier A and vernier B consisting of two scales. Okay now, one is main scale, another one is vernier scale. So in the vernier we are having 20 minutes accuracy. Okay now, so that is our least count. So by taking the average between vernier A and vernier B, we can get the horizontal angle. Okay now. So this is with respect to our upper plate and the lower plate. So here we are having two screws. One is upper clamp screws, another one is lower clamp screws. If I am going to tight the upper clamp screw and going to lose the lower clamp screw, I can able to rotate the instrument without changing the readings of vernier A and vernier B. Okay. So for example, this is our vernier A. Here I am having some values. Okay now. So if I am going to lose only the upper clamp and if I the my if I am going to lose only the lower clamp and the upper clamp screw is in tight condition. Okay now. Now I can able to rotate my instrument with respect to vertical axis. Okay now. In the horizontal plane so that the readings of verniers cannot be changed. Okay now. Now my lower clamp gets tightened and the upper clamp gets loosened so that if I can able to rotate my instrument with respect to vertical axis in the horizontal plane. Okay now, so that the readings of vernier A and B can be changed. Okay, so this is the things are related to upper and lower plates. Next, a transit vernier theodolite consist of the following essential parts such as leveling head, lower circular plate, upper plate, telescope, vernier scale, T-frame, plumb bob, tripod stand. So T-frame is nothing but here one frame we are having. Okay now, so that is called T-frame. Okay, so these are all the essential parts which we are having in the theodolite. So plumb bob is used to uh, do the centering process so that the instrument center and the ground point center should be oriented exactly. Okay now, so that our instrument has to be placed over the station points exactly. Okay now, tripod stand is used to hold the instrument in their position. Okay now, so without tripod we can't do the surveying by using Totalites. And I already said telescope consisting of both eyepiece as well as object piece. Okay now. And vernier scale, we are having horizontal vernier scales, that is vernier A and B. And vertical, in vertical circle we are having, okay now, that is called vernier C and D. So here we are having 0 to 180-degree in vertical scale. Okay, vertical circle. Okay now, here 0 to 180-degree we are having the angular values, that is with respect to telescope position. Okay now, and our horizontal circle or in the upper plate we are having vernier A and B. This is to used to measure the horizontal angle. Okay now, uh, that is 0 to 360-degree we are having, both the scale having the least count of 20 seconds. Next, terminologies used in the theodolite surveying, that is first one is centering. So centering means setting the theodolite exactly over the instrument station point so that the vertical axis of the instrument has to be lie immediately above the station point or station mark. Okay now, it has to be done with the help of plumb bob suspended from the small hook which available at the beneath surface of the theodolite. Okay, now and it is exactly oriented with the vertical axis of the instrument. Okay, now so with the help of the plump up we are going to do this centering process. Okay, next, transiting. So transiting is the process of rotating. Okay, rotating the telescope in the vertical plane. Okay, now so that the telescope can be rotated like this. Okay, now so this process is called transiting. With respect to 180 degree we are going to rotate it. Uh, so in the figure we are having some arrangement like this. Okay, now that is one, two brass knobs are placed over the theodolite. Okay, now sorry, placed over the telescope. Okay, now if it is in the top position, okay, now that is called telescope normal position. Okay, now so that if I'm going to rotate it, so that those two rings or those two knobs will comes uh, under the position. Okay, now under the telescope. Okay, now so that that process, okay, now so that the plane view has to be viewed over the surface of telescope, that is called telescope inverted. Okay, now so this process, okay, now is called transiting. So that we, the this if the telescope is like this, okay, now then we are going to rotate like this is called transiting. So transiting can be done like this or like this, both are same. Okay, now next, swinging the telescope. So it means turning the telescope about its vertical axis. Okay, now in the horizontal plane is called swinging. Okay, now the swing may be left or right. Okay, according to the telescope is rotated clockwise or anti-clockwise. Okay, now so this is called swinging the telescope. Okay, now so like um, our instrument has been rotated like this with the help of telescope, that is called swinging. Okay, then face left observation. I said no, the vertical circle. So the vertical circle is placed on the left side of the observer during the measurement. Okay, now that position of observation is called face left observation, and the position is called face left. Okay, that can be done with the help of our instrument, that is I said no, the knob of the telescope here in the figure. So here the vertical circle is available here. Okay, the vertical circle is available here in the, okay, in this figure we can see. So here the vertical circle is available. Okay, now if in this position, if I'm going to see, this is my left side of the vertical circle is oriented to my left side. Okay, now so that whatever the observation I'm going to do or I'm going to take, that kind of observation is called face left observation. Similarly, face right observation. Okay, now if the vertical circle is right side to the observer, then it is called face right observation, and the position of the circle, vertical circle, is called face right. Okay, next, changing the face. So changing the face in the sense, uh, that is the vertical circle is to be changed from left side to right side and right side to left side, corresponding to the observation, that is called changing face. Okay, now how the way we have to done. Okay, now for example, this is my telescope normal position, so that my points, okay, now that is the knobs are at above side. Okay, now at the top of the telescope. Okay, now so that first I have to rotate my instrument so that the vertical circle should to be here. Okay, now so if I'm going to rotate my instrument within the horizontal plane, okay, now automatically it will come in the face right observation. Okay, So if I want, this is called changing phase. If once again I have to do, what should I do means, I have to rotate my telescope, okay now, and I have to rotate like this, okay now. That is, I have to do transit process and swinging process, okay now. Then only I can get the phase changing process, okay. So the changing of vertical circle from left side to right and right side to left is called changing the phase. Next, line of collimation. It is also known as line of sight, okay now. So the imaginary line joining the intersection of the crosshairs in the diaphragm to the optical center of the object class and its continuation is called line of collimation. Uh, so I already said we are having the diaphragm. In the diaphragm we are having the crosshairs like this, okay. So the center of the diaphragm, okay now, and the optical center of the object class, okay, the continuation of this imaginary line is called a line of collimation. Next, axis of telescope. It is also an imaginary line joining the optical center of the object class to the center of the eyepiece, okay now, is called the axis of telescope. Next, axis of level tube. It is also called as the bubble line, okay. It is a straight line tangential to the longitudinal curve, okay. Curve level curve level tube at the center of the tube. It is horizontal, okay now, when the bubble is in the center, okay now. Next, vertical axis. It is the axis about which the telescope can be rotated in the horizontal plane, okay now, rotated in the horizontal plane. Next, horizontal axis. So first I will show the vertical axis. So this is our vertical axis, so that I can able to rotate my telescope in the horizontal plane like this, okay. I can able to rotate the telescope in the horizontal plane. Next, horizontal axis. So it is the axis about which the telescope can be rotated in the vertical plane. It is also called as Trunian axis. So the telescope, if it is, this is the telescope, then I can rotate the telescope in this direction, okay, either upside down or downside up, okay now, likewise vice versa. If I'm going to rotate like this, then that is called horizontal axis, okay. With respect to its axis I'm going to rotate it. So the another name of our horizontal axis is called Trunian axis. Next, so this is the graduations which are likely to have in our instrument, okay now. Even it is Vernier A or Vernier B or Vernier C or Vernier D, we can have like this arrangement, okay now. So this is called our main circle, okay. This is our Vernier scale, this is our main scale, and this is our Vernier scale. So how the way we have to read the readings, okay now. For example, this is our index, okay now. In front of the index, this is consist of 0 minutes, okay now, 5 minutes, 10, 15, 20, and here whatever the small measurements, no, that is called 20 seconds, 40 seconds, then 1 minute, 1 minute 20 seconds, 1 minute 40 seconds, 2 minute, 2 minutes 20 seconds, 2 minutes 40 seconds, likewise, okay now. So how to read the Vernier scale reading, that I will explain here, okay now. First, in front of this index line, okay now, what is the reading is available, that we have to check it. Here it is in degree and minutes. Here we are having degree and minutes reading in the main scale, okay now. In the Vernier scale we are having uh, minutes and seconds, we can able to read it, okay now. First, in front of the index, what is the value we can have here. So 10 degree 20 minutes we are having. So 10 degree 20 minutes we are having. Okay, now we have to check which line is coincided exactly with the main scale reading and the index scale reading. Okay, now so that we have to check it. So here, so here the line 20 minutes is exactly coincided here, so that I have to note down this reading. So 20 minutes and 00 seconds, so that my Vernier scale reading is 10 degree, 20 20 40 minutes. I have to add, okay now, and 00 seconds. Okay, instead of this line, if this line is joined or this line is exactly oriented, then what should I have to take? So 10 degree 20 minutes plus 20 minutes 20 seconds I have to take, so that my angle becomes 10 degree 40 minutes 20 seconds. Okay now, so this is the way we have to read the Vernier scale. Okay now, even it is in horizontal plane or in vertical plane, whatever it may be, this is the way to read the Vernier scale readings. Okay, so the fundamental axis of theodolite and their relationship. So this is our vertical scale. Here I can read my vertical angle. Okay, now here Vernier C and Vernier D are placed. Okay, so this is my horizontal axis or Trunnion axis. Okay, now, and this is at the center of the vertical circle. Okay, now, and next, horizontal plane. So with respect to this vertical circle, I can rotate my telescope in the vertical plane as well as in a horizontal plane. Okay now, so here I can rotate with respect to my telescope in the vertical axis. Okay, and next one is, sorry, vertical plane. Next one is horizontal axis. So this is the horizontal axis. Next one is vertical axis. This axis has to be passed at the center of our horizontal plate or horizontal circle. So the horizontal circle consists of upper plate, lower plate, tri-batch, that setups. Okay now, and here the Vernier A and Vernier B has been attached in to measure the horizontal angle, so that my telescope has to be has been rotated with respect to vertical axis in the horizontal plane. Okay, so this is the fundamental axis of theodolite and their relationships. Next, the adjustments of a theodolite. So whenever we are going to the field, we should do some temporary adjustments. Okay now, then only the instrument has to be get ready for taking the measurements. Okay now, uh, so those temporary adjustments are, one is setting up and centering. So that is nothing but the instrument is to be placed over the exact station point. Okay now, so that is called setting up. That is with respect to tripod we are going to place. Okay now, and the instrument axis, that is vertical axis, and the station point have to be oriented exactly. Okay now, for that, with the help of plumb up, or else we are having some class in the instrument. Okay now, by viewing that we can get or we can bisect the ground point. Okay now, so likewise we have to do by adjusting the tripod by moving front and back and left and right. Okay now, so this is the process called setting up and centering. Second thing, leveling. Okay now, so leveling in the sense we have to make the bubble, okay now, is at center, either plate level or altitude bubble. Okay now, corresponding to horizontal angle measurement and vertical angle measurement. So that process is called leveling process by adjusting the foot screws. Okay now, so for that, as like our dumpy level, okay now, there are parallel and perpendicular adjustment. So here we are having 3 foot screws. Okay now, first the telescope to be oriented with any 2 foot screws, so that we have to adjust the foot screws, 2 foot screws simultaneously, either inner side or at outer side. Okay now, so that the plate level all altitude bubble is to be gets its center position. Okay now, then after we have to rotate our instrument telescope. Okay now, so that the telescope is at perpendicular position. So like this is at perpendicular position, and our plate level or altitude bubble is here. Okay now, so by adjusting either inside or rotating, sorry, clockwise or anti-clockwise. Okay now, by adjusting the foot cruise, the third foot cruise, the bubble has to be get center position of its level. Okay now, so by doing this process alternatively, okay now, so that the bubble is to be placed at exactly the center position at all the rotation. Okay now, so this one we have to ensure, that process is called leveling. Okay now, then third one is elimination of parallax. So here, by adjusting the eyepiece, that whatever the diaphragm, that is crosshairs inside the diaphragm, that should be, we can able to view clearly. Okay now, by adjusting the eyepiece either clockwise or anti-clockwise. Okay, by adjusting the eyepiece we can make the diaphragm, that is crosshairs, to be visible clearly. Okay now, that process is called, that process, along with that, by adjusting the object piece. Okay now, so that whatever the object in front of the telescope is to get clear visibility. Okay now, so this process is called the elimination of elimination of parallax. Okay, thank you.